Good day, students. So we are starting class for day 8 today. And what are we going to do today? Properties of matter solid. Okay. And which property is that which we are going to study? That is elasticity. What is elasticity actually? A property due to which an object regains its shape and size after the removal of external force. Okay, what is the meaning of that? If suppose that I am taking on wire here. There is a wire. Okay, this end we will make fixed. And from here we applied force. So because of the application of force, what we are trying to do? We are trying to increase its length. Right? Once we are removing this force, there is definitely some increase in length. But once we are removing the force, it will come back to its original shape and size. And if it does so, we will say that this is elastic material. Okay, similar then, we have seen in spring also. This is a spring. You applied the force, what happens? Extension happens. And once you remove this force, spring will come back to its original shape and size. We say spring is elastic. The same way, this wire is elastic if it comes back to its original shape and size. So, which defines that this is elastic material, and that property is called elasticity. Okay, so this elasticity actually we define in terms of two more things, two more properties, let's say. What are those two properties? Those properties are called stress and strain. Okay, those are called stress and strain. Stress and strain. Okay, so first thing is what stress is. What property is stress? Now, stress is whenever you apply an external force on an object to increase the length. What happens? Inside that object, there are molecules, we all know that. So, when you are trying to increase the length means you are trying to increase the separation between the molecules. And molecules oppose that. Molecules attract other molecules. So, there is opposition. Okay, so stress is due to that opposition only. So, we define stress as restoration force per unit area. Restoration force per unit area. Normally, it is equal to external force that you are applying per unit area. We have seen this is spring, right? When you are having a spring over here. Okay, suppose this is the handle. You are applying F force from here. So immediately spring force will come. And in equilibrium, what we write? Fs equal to F. So apply this on the wire. F by A, F by A. That's exactly what I am saying. So when stress we are writing as restoration force per unit area, but its value is equal to the force applied per unit area. For external pressure, you say. Okay. Its value is equal to what? External pressure. Stress is equal to external pressure. But is stress actually external pressure? No, only value is equal. Both have different meaning. Stress is because of molecular force inside, molecular force per unit area. External pressure means is what you are applying from outside. Okay, right? This is stress. Same way now strain. What is strain then? Now when you apply the stress or external pressure to change the length, obviously length will change or dimension will change. So strain is change in dimension of the object. Change in dimension to original dimension. It's a ratio. Change in dimension to original dimension. Okay. Now stress is external pressure, so its unit also will be pressure unit only. That means Pascal or Newton per meter square. Okay. Its unit is Pascal or Newton per meter square. Where is this? This is a ratio, so it's dimensionless. Okay. This is dimensionless and unitless as well. Its unit is same as pressure unit. What is pressure unit? This is Newton. So mLT minus 2 by L square. So its dimension will be m L minus 1 T minus 2. M L minus 1 T minus 2. Okay. So these are the two properties through which we define elasticity. How we are defining? Let's see. There is a law which gives us relation between stress and strain. Okay. So what it says? What is the law? Hooke's law. And it says that stress produced is directly proportional to strain. Okay, that means whatever change in length or change in area or change in volume or change in dimension that is happening in an object, that is directly proportional to the stress you are applying. That means more the force you apply, more will be change in length of the spring. Correct or not? Exactly same thing. More the stress is there, more is strain. So if you make the graph, here, okay, so this is x and y axis, and this one you put here stress, I put here strain. Okay, so what Hooke's law is saying? Hooke's law is saying that they are proportional, right? They are proportional. So how will be the graph? Graph will be a straight line, like this. Okay, it will be a straight line here. Stress is proportional to strain. Then, how to measure elasticity? But so he says that when we are saying stress is proportional to strain, stress is proportional to strain, then remove the proportionality. So stress equal to K times strain. So K is stress by strain. And what is this K? K is Hooke's constant. K is Hooke's constant, or K is modulus of elasticity. This is modulus of elasticity, or you can say measure of elasticity. Measure of elasticity. Now what is the meaning of measure of elasticity? Measure of elasticity means is if K value is more, body is more elastic. Okay, if K value is more, body is more elastic. If K value is less, body is less elastic. How to measure K? There is a stress and strain graph we have. Okay, so if I see here, slope of this graph gives me K value. Slope of this is K value. Slope means tan theta. You can see if this is theta here, tan theta will be giving us what? Stress by strain only. Or you can say change here, change in stress by change in strain. Correct. So tan theta here will give us modulus of elasticity. If there are two graphs I make, okay, not here. So if I suppose I make one more line here. There's one more line. Okay, and if I say that out of the two wires, which is more elastic? We will say wire 2. Reason? Angle is bigger. This is theta 1, this is theta 2. Theta 2 is greater than theta 1. Or you can say tan theta 2 is greater than tan theta 1. So that means K2 is greater than K1, because K2 is measured with the help of tan theta here. So this is more elastic than this one. Understood that? This is more elastic than this one. Now, based on this one, if I ask you, if steel is more elastic or rubber is more elastic? Steel is more elastic. Okay, steel is more elastic. So why? Steel is more elastic than rubber. Answer is why? Because we are saying that K measures the elasticity and K is stress by strain. So which one, steel or rubber? Change in dimensions is easier to produce. Rubber. It's very easy to produce change in dimension in rubber. With lesser strain? Yes. Right. If suppose that 1 centimeter change I want to produce in rubber wire and steel wire, which one is easy to produce? Rubber wire. With a less force? Yes, with a less force. So then what we will say? Strain is same in both, right? But stress will be more in steel because you have to produce or you have to apply more force to produce the same strain. How much strain we want to produce? 1 centimeter. To increase the length of 1 centimeter of rubber wire, you have to apply very less force. Whereas in steel wire, you have to apply very large force. Correct? So, which is more elastic? Steel. That is the reason why railway track is made from steel, not from rubber. Okay. And why elasticity is more important? Because every structure is made from elastic material. Suppose we talk about a bridge. So many vehicles are passing. So much force is being applied on those structures. What happens? Deformation will happen, no? Obvious. So then it has to come back to its original shape. If it doesn't come, then it will collapse. So that's why elasticity is important. And second thing is, which material is more elastic? That also is important for us to know. Okay. So which requires more force to produce smallest of deformation? That body is more elastic. So here, that's why steel is more elastic than rubber, because for producing the same change in length, you have to apply more force in steel as compared to rubber. That's why it's more elastic. Okay? Right? Okay, let's move ahead. The stress strain graph. Let's see what happens in that. So we saw that stress is directly proportional to strain. This is what Hooks told us. Is it always? Answer is no, because this is the graph you can see. In this one, from this point, if suppose this is O, to this point there is A. I can say that, okay, there is a straight line. So here I can say stress is directly proportional to strain. Okay, so this OA here is called proportionality limit. This is proportionality limit. Proportionality limit. Okay, then what happens in this one now? Now in this one you can see that here if I have increased the stress by this amount only. This is the stress. But strain is more. Comparatively, we have increased stress less, but strain is more in this one. Strain produced or change in strain. Change in strain is more than change in stress. Okay, but in this region also there is one speciality. What speciality? Like suppose if I explain you the speciality of OA. In this one you are applying the stress. Stress we are applying means external force we are applying so that we can deform the body, right? So if in this region from O to A, if you remove this external force, the stress, what will happen is body will regain its shape and will come back to O. If this is the starting point, then within OA, anywhere you remove the stress, body will come back to O. Fine. Now let's talk about AB. In this one, we know that stress is not proportional to strain. But still, within this range also, if we are going to leave the external force or applied force or stress, body will regain their shape. Okay, that's why this AB is called elastic limit. Okay, so till B point, wherever you leave the external force, applied force, body will regain their shape. From B to this point, so this is C. This is called plastic region. What is this plastic region? Plastic region means is if you have extended the stress up to this point, there will be always some deformation in the body. It will not come back to original shape. Okay, it will not come back to original shape. There will be deformation. And here, let's say the C point is there, where we can say this is breaking point, where the object or particularly wire is going to break. Okay, more the plastic region, more ductile is the material. Ductility means we used to draw wires from that. Okay, more plastic region means more ductile is the material. More plastic region means more ductility. Less plastic region means object is brittle. Less ductility means brittle. Indicates the object is brittle. Okay, clear? Okay, fine. So what we have here also I have written. Ductile material means it has very large plastic region. Brittle material means it has very small plastic region. Same point. But what is this? If an object obey Hooke's law, it is elastic material. Definitely it's elastic. Okay, compulsory. Elastic. If an object is obeying Hooke's law, it is compulsory elastic. Second one is what? If object is elastic, it may follow Hooke's law. What is the meaning of that? The reason is because here also this object is elastic. But is it obeying Hooke's law here? No. So there is a possibility that even if the object is elastic, it may not be following Hooke's law. Strain will be more than stress. Okay. One more point. This plastic region means what? In this one you see that hardly we are increasing the stress, but how strain is? Okay, so in this region, material starts flowing like a fluid. Okay, that's why we are drawing the wires, right? In ductility. In plastic region, wire starts flowing. Strain is a lot more than the stress. Okay. Right, students. What next? Different modulus of elasticity. So we have different modulus of elasticity and we have different modes of stress and strain also. So first I will tell you about stress and strain, then we will go to modulus of elasticity. So let's see, we are doing stress and strains here. Different type of stresses. Stresses. Okay. So first you have to understand there are three type of objects on which we try to apply the force, external force. One, linear. Linear means you have a wire and you want to apply the force on wire. Where will be the change happening? Along the length. Okay. Then if suppose that I am going to apply the force on two-dimensional object like plate is there, rectangular plate, circular plate, ring. So in that one where change will be there? In area. If suppose there is three-dimensional object, then where change will be coming in volume. Right. So depending on which type of object we are applying the force, stresses are there. So three types of stresses are there actually. What are those? One, longitudinal. Longitudinal means you are trying to change the length, whether increase or decrease. Second one, bulk or volumetric. Volumetric stress. And third one we call as shear stress. Okay, this is when force is applied along length. Force is applied along length. Okay, and maximum questions will be on this kind of stress on. Longitudinal also there are two types of stresses. Okay, what? When you're trying to increase the length, then we call it as tensile stress. Second one, you're trying to decrease the length, you are compressing it. So then stress is compression stress. Okay. So longitudinal stress also two types. Two types of longitudinal stress. Okay, tensile and compressive. Tensile and compressive. When tensile? For increase in length. Okay, and when compressive? When you try to decrease the length. For decrease in length. right? So when you try to increase the length, the stress, we call it as uh, longitudinal one. So how it is, let's see. Where we can have, okay, fine. So, and this is the wire. Okay, on this one, suppose I apply the force. How we are applying the force? Like this. This is the force. Both sides we are applying. What we are trying to do? We are trying to increase the length. So stress will be called tensile stress. And what is tensile stress value? F by A. Force by area. That's what we saw, no? Force by area. What is force? F. Actually, it is internal force per unit area, but I told you that internal force is equal to the force applied. Okay, so F by A. In both values will be this only. In one, you are trying to compress the length of wire, and another one you are trying to increase the length of wire. Okay, fine. Then there is volumetric stress. Volumetric stress is what then? Let's see. So volumetric stress. Okay, now volumetric stress acts on what? This volumetric stress will be mostly on liquids and gases. Not like solid you can't have, but mostly we'll discuss in liquids and gases. Now suppose that this is a bubble in atmosphere. So what happens is, from external side, there is atmospheric pressure is acting in this way on entire bubble. And now what this atmospheric pressure is trying to do? It is trying to compress it. Okay, so volumetric stress is this atmospheric pressure only. Yes, stress is actually pressure, right? Okay, so this is directly volumetric stress. Okay, third one is shear stress. Now what is this shear stress here? Okay, so let's see what shear stress is. So shear stress is when you apply the force tangential to the area. So far how we are applying? Perpendicular to area. Which area? This area. You applied the force perpendicularly. But this time I am saying you are applying the force tangentially. Now suppose we take this over here. Okay. And we try to make a three-dimensional object from this. Okay, this is the three-dimensional object. So now what I am going to do is, I am going to apply the force along the area. Where? Here. Here I am applying the force on this area, and that too parallel. On this area I am applying the force parallel. How? Like this. This is the force. So in this case, the stress produced is called shear stress. And what is shear stress? Again F by A only. No change in that. Which area? This its value. So this is called shear stress. Value is same, unit is same, Newton per meter square. Okay, no change in the unit, but all three are different type of stresses. Okay, all three are different type of stresses, right? Okay, fine. Now what? We learned stresses. Now strain. Strain also we have to see. Okay, shall we see it in different slide? I think that will be better. So, shall we go it in the end? You may get any slide in the end. Oh, too many are there. Okay. So here, types of strain we will see. So like types of stresses are three, types of strain also three. First is longitudinal strain. What is longitudinal strain? Change in length by original length. Okay, longitudinal strain is what? Change in length by original length. Change in length by original length. Delta L by L. Right? Volumetric strain, change in volume by original volume. But in this one, this change in volume happens to be negative all the time. Why? Because atmospheric pressure is trying to decrease the volume of the bubble all the time. So final volume will always be less than initial volume. So delta V is always negative. Okay. Change in volume to original volume. What it is? Minus delta V by V. Now interesting is third one. Now this is all okay because you are trying to put pressure so that volume you can decrease, or you are applying the force so that you can increase the length. But shear strain is the most interesting one. Now in this one, what is happening? Okay, shear strain, when you apply the force, okay, when you are applying the force, okay, so this is how we took the object, right, like this, and then we are applying force on this one. So it's like this, and we are applying the force on this top surface, right? We applied the force on this top surface, like this. So what happened? The top surface actually displaced. Below surface is all tight. You just make it fixed. This is fixed here. When you applied the force, what will happen? It moves ahead. So then, if you try to make it maybe something like this. Okay. It's gone like this. Right. It has become in this way. So your top surface, in fact, bottom surface is fixed, as I said. This is fixed. Top surface is gone. It is difficult to show in this one. Here only I'll make, okay. In this one only I'll try to show you. Right. So now what has happened? This was the surface, okay. This was the surface. First surface only I am showing you. Suppose this is ABCD. Oh. A, B, C, D. Now because you applied the force like this, now what happened? The D point has moved to this point and C point has moved to this point. Okay, it's like this now. So this is the deformation that is produced. This is the deformation. So shear strain is measured in terms of angle, this theta. This theta. Okay, so we call this as tan theta equal to dd dash by this length. Maybe this length is L, we will say L. dd dash by L. This is shear strain. This is shear strain. Okay, so these are stresses and strains. Now based on them only, we are here trying to define what? We are trying to define modulus of elasticity. Okay, we are trying to define modulus of elasticity. So where it is, where we have to go, right, here we are. Okay, so modulus of elasticity. Now we have seen all types of stresses also, all types of strains also, and modulus of elasticity is also what? A ratio of stress to strain, right? So see then what we can do. Okay. Okay, so different type of modulus of elasticity. The first one is Young's modulus of elasticity. Young's modulus, which we represent with Y. What is this now? This is ratio of longitudinal stress to longitudinal strain. Longitudinal stress to longitudinal strain. Right, and maximum questions we are going to solve on this only. Longitudinal stress means what? F by A. Longitudinal strain means delta L by L. So, Y equal to FL by A into delta L. Okay, what is that? Young's modulus. Second one, bulk modulus or volumetric. Okay, bulk modulus. We represent this with beta. What this is now? This is equal to volumetric stress to volumetric strain. Volumetric stress to volumetric strain. What is volumetric stress? We said external pressure. And volumetric strain minus delta V by V. It will become minus P naught V by delta V. Okay, final one, shear modulus or modulus of rigidity. Shear modulus or modulus of rigidity. And we represent this with eta. Sometimes in some books it will represented as K also, but mostly it is eta. Now what is eta equal to? Shear stress by shear strain. Shear stress means tangential stress. Okay. Shear stress by shear strain. So what we saw, shear stress was F by A and shear strain is represented with theta. So F by A by theta. This is modulus of rigidity. This is how we define them. Okay. Let's see what next is there. Graph between delta L and L. Oh, that is question now. So we have to make a graph. Okay, fine. So graph we are going to make between delta L and L. First, let's have the relation. This is delta L and this is L. And what is given? F and Y are constant. Now this question is asked in one of the NEET previously. Okay. So graph between delta L and L when F and Y are constant. So delta L and L what? Just see that previously we have written something. See? Delta L by L. So delta L by L, if I see from here, it is F by AY. Okay. Delta L by L is equal to F by AY. He says F and Y are constant. So that means I can say delta L by L is proportional to 1 by A. Now A, what shall I do with A? Area, no? A means area, cross section area of the wire. Delta L by L, he is asking me, he is talking about longitudinal stress. And remember, maximum question will be on Young's modulus and longitudinal stress and strain. Okay. So delta L by L is asking, here is area, what shall I do? Question is, if you are going to increase the length of any wire or you are going to decrease the length of the wire, what is the constant thing in that? Young's modulus is constant, yes. Volume is constant. If you decrease the length, area will increase. If you increase the length, area will decrease. So what is constant? Volume. Okay, so if there is volume, then I can write this area as volume by length, no? This is volume. So what will happen? We'll write delta L by L as proportional to, in place of this, volume by length, so it will become L by V. And V is again constant. What is V? Volume, and volume is again constant. So we can say delta L is proportional to L square. Delta L is proportional to L square. That means it will be a parabola. So how will be the graph? Graph will be like this. Open parabola. Okay. Then see the next question. Graph between delta L and A if f and y are constant. Then okay. At least this is true here also. We can write delta L by L equal to f by ay. Definitely we can write. Then f and y are constant anyhow we know. So delta L by L is proportional to 1 by area. Now how to write 1 by area? Same way. Okay, in place of area what I can write? But here I have to find delta L by A. Okay, fine, no issues. So delta L by L is proportional to 1 by A. F and y are constant. Okay, but here relation is different. Here graph I have to make between delta L and A. So here length I have to change because length is not required here. So what I can write as length? Length I can write V by A. Okay, so delta L by V by A, or directly first make it like this, L by A. Okay, then delta L equal to V by A by A. So that is V by A square, and V is constant we all know. So here is coming delta L is proportional to 1 by A square. So again it's not a straight line. Okay, so this relation will be what? If we have to make this relation. Okay, so let's make the graph first. So here I am making a smaller one. Okay, then y-axis also we will make. Right, now what? So it says that there is inverse proportionality is there. If A is on the higher side, delta L will be less. If A is on the smaller side, where is A? Here. And here is delta L. So here is A 0 side. So that means delta L will be very high. As A increases, delta L is going to decrease. So it will be like this. So delta L and area graph. Delta L and L graph. Okay. Right. One more question is there. Just a minute. Let's take a break of a minute. Right. Two wires are given. One of diameter is 2r, one of diameter is 4r. What is given? And length is same. Find ratio of their change in length if applied force and Young's modulus is same. So applied force is same. He is asking change in length, that is delta L. Okay. So what is the relation? What is the formula for delta L? FL by AY. Remember that. Normal formula is Young's modulus equal to stress by strain. From there also you can get it. Okay. Delta L equal to FL by AY. He is asking ratio of their change in length. So I am saying that delta L1 by delta L2. Okay. F and Y are same. Okay. So F L1 by A1 Y. And here F L2 by A2 Y. So F and F gets cancelled. Y and Y gets cancelled. So what we have now? Delta L1 by delta L2 is actually equal to L1 by A1 by L2 by A2. Correct? So L1 by L2 into A2 by A1. Now what we have? L1 and L1 are same. So this L1 and L2 is getting cancelled. A2, its radius is 2r. Okay. So pi into 2r whole square by pi into r whole square. The answer is 4 is to 1. Answer will come 4 is to 1. Correct? Right? See next one then. What will be the answer of previous question if volume of both wires is same? Okay, fine. In this case, if volume we are making same, this is V1 and this is V2. Okay, so if volume is same, so definitely length cannot be same. Okay, because areas are different, no? Okay, so here is pi, this one, pi r square into L1 is equal to pi into 2r whole square into L2. This r square and this r can cancel. So L1 by L2 in fact is coming 4. L1 by L2 is coming 4 in this case. Right? What else is there? So let's put it. L1 by L2 is 4 and area also. Correct? Area is also A2 by A1. Now L1 by L2 into 8 because F and Y is given same. In the next question also, what will be the answer if previous question if volume of both wires is same? Correct? So F and Y is same, so Fi is getting cancelled. What you have? L1 by L2 into A2 by A1. L1 by L2 came out what? 4. So L1 by L2 is place 4 and A2 by A1 is already 4. So what will be the answer? Delta L1 by delta L2, which is L1 by L2 into A2 by A1. This is also 4, this is also 4, so answer is 16. 16 is to 1. Okay, clear? Alright, then Young's modulus of elasticity. We have studied about this. Young's modulus is what? Longitudinal stress by longitudinal strain. Okay. Now, what and how the changes can be brought in Young's modulus? That is written over here. This says Young's modulus decreases or increases in temperature. So when you increase the temperature, it is relatively easier to change the length of the wire if the temperature is increased, right? But how we define elasticity? We said that more force if it is required to produce unit change, then it is more elastic, right? But by increasing the temperature, what you are doing? It's making easy to change the length. So that's why we are saying Young's modulus decreases on increasing the temperature. Second one, increases on adding elastic impurities. Now suppose that one object is there which is less elastic and we want to make it more elastic. So what shall we do? We put some impurities in that which are elastic in nature. So because of that, what will happen? Its elasticity we can increase. Okay. Third one, increase on hammering. So when you hammer it, what are you doing? You are making this molecule to concentrate at one place. When they are going to concentrate at one place in that particular area, molecular forces will be more. So elasticity will increase in that area. Okay. Finally, for a perfect solid, Young's modulus is infinite. For a perfect solid, it is impossible to produce any kind of deformation. So it is having elasticity or Young's modulus of elasticity is infinite for that. Okay, one more question is there. So based on what we studied right now, you can see that this is here is y-axis and x-axis is given, and which temperature is higher he is asking, and this is Young's modulus are given. Okay, Young's modulus are given. I think it should be stress and strain over here. Okay, this should be stress and this should be strain. Okay, so we can see that this angle is more. This angle is more means y1 is definitely greater than y2. We know that. Okay, y1 is greater than y2. Now we saw that at higher temperature, Young's modulus of elasticity decreases. So we are saying y2 is less, y1 is more. So that means definitely here temperature is less than temperature. Okay, which temperature is higher? So that means for same wire you can say. For same wire. So we can say T2 is more than T1. Why? Because here Young's modulus is less than Young's modulus here. Okay. Right. Find final length of wire. Find final length of wire of initial length L, area A, Young's modulus Y on application of force. Okay, simple question that is. So there is one wire. Okay, there is one wire. Okay, this is one wire here, and this wire length is L, area is A, Young's modulus is Y, and you are applying the force F. Okay, so we apply force F from here, and let's make it fixed at the top. Okay, so you applied force F. Okay, so what he wants? Final length of the wire. So first let's find out what is change in length. Change in length I told you already, FL by AY, right? But he is not asking delta L, he is asking final length. So what shall I say? L final minus L initial is this. Right or not? So final length means what? L initial plus FL by AY. So initial length is L. So L plus FL by AY. That will be the final length. Remember that. Sometimes they ask you final length, you calculate change in length and move ahead. Final length is this. Okay. Alright. Next. Next is same question. But instead of force, they have one bob which is attached with this one. Okay. And suppose in this case I say instead of this area, say that its radius is R. Okay, its radius is R. Don't take area. Take its radius. Then find change in length. So delta L formula we already know, FL by AY. So what is F here? mg. This is mg. Okay, length is L. Area pi r square y. mgl by pi r square y. That is the change in length. Right? Okay. Right. Now this wire is not having any load attached with that and we are not applying any force on that one. But it is having weight of its own. This is mass. So because of its weight, what will be the change in length? Okay. So first thing is, if this is uniform, then we know that the weight of this is acting at its center of mass here. That is mg. And this mg is trying to deform how much length of the wire? L by 2. Okay. Where mg is acting? On this portion only, no? So what will be delta L? Delta L formula is not going to change. It is same FL by AY only. But F is what here? mg. And mg is trying to increase which length? Total length or L by 2? L by 2. So here is L by 2. By same area and y. So our answer here is mgl by 2ay. In the previous case, it was mgl by ay because weight was acting here, it was trying to increase entire length. Here, weight is here, which is acting on L by 2 length. Okay. Alright. See this now? Two wires are given. This is having Young's modulus Y, radius R and length L. He says this wire breaks at weight W. Weight W means is force. Okay. The force that you are applying is W. Find weight W here at which this wire is going to break. Young's modulus is given same. Young's modulus, that means the material of this wire and this wire is same. Right. So breaking stress will be same for both them. If they are of the same material, then breaking stress should be same. Because y1 equal to y2 given, no? So breaking stress is same. Breaking stress is same. Okay, that means in this one what should be weight? We don't know, but we can write it as, in this case, this is W by pi r square. Should be equal to W1 by, what is area? Radius is given 2r. So pi 2r whole square. Pi cancel, r square and r square is gone. W equal to W1 by 4. So W1 should be 4W. Simple. Okay, breaking stress means what? The stress at which the object is going to break. Okay, the same material, so breaking stress we are taking same. Okay. Alright, what next? Find ratio of change in length for wires. Okay. So how much change in length will be there? In the same question. We didn't talk about change in length in this one. Yes or no? Now he is asking that. Okay. Change in length, delta L is what? FL by AY we know. FL by AY. Correct. Now we already have said that at breaking stress, this is same. In fact, Y is also same for both wires. So delta L is actually proportional to L1 or L. So delta L1 by delta L2 is actually equal to L1 by L2. And what is L1 by L2 here? L by 2L. So L by 2L. That means answer is 1 by 2. Okay, because we took stress same, no? Same stress and Young's model is also same. So delta L is proportional to L. Right? Okay, let's see another question. Two wires are there again. Young's modulus is same, radius is R and 2R, length is 2L and L. What is ratio of extension if same force is applied in both wires? Same force you are applying. Okay. What he is asking? Ratio of extensions. That means delta L1 by delta L2. So delta L is FL by AY. So both are having same Young's modulus. So just remove this one. Both are having same force. So remove this one. So that means delta L is proportional to L by A. Proportionality is L by B. So delta L1 by delta L2 is equal to L1 by L2 into A2 by A1. That's all. L1 is what? 2L. This is L into A2. A2 means 4 pi r square. Actually pi r square only I am doing, but radius is 2r, no here. So 4 pi r square by pi r square. Pi r square cancelled, L is cancelled, this is 8 is to 1. If the same force you are applying, then ratio of extension is 8 by 1. Second one, what is the ratio of extension if same strain is applied? Same strain is produced. Okay. So strain is same. Then what we have to do? Ratio of extensions. Young's modulus is same given. Strain also same. Okay, fine. So let's see where we can do. Okay. So extension again, and delta L is FL by AY we know. Correct? Okay. So same strain, that means delta L1 by L1 is equal to delta L2 by L2. So delta L by L actually is what? F by AY, right? So it means we can write this as F1 by A1 Y equal to F2 by A2Y. Correct only. Now this is same. This is cancelled. So I can write for the second question delta L1 by L1 equal to delta L2 by L2 is actually equal to F1 by A1 by F2 by A2. If same force is applied as in the question 1, we can find because areas are given. Areas are given, we can find it. Okay. So if F1 is F1 and F2 are same, then answer will be A2 by A1. So A2 is what? 4 pi r square and this is pi r square. So 4 pi r square by pi r square. So answer is 4. Same strain and same force. If suppose stress is also same, if strain and stress both are same, then what will come? 1 by 1 will come, right? Because this is ratio of strain, which is equal to ratio of stress. If stress is also same, it will come as 1. But in this question, it is not asked from you. Okay, let's move ahead. Bulk modulus. We have discussed this. Bulk modulus is what? Minus external pressure or delta P by delta V by V. So we can say beta minus beta, this I am writing as dV by V equal to P external. Okay, this dV by V can we also write in terms of density, because density is mass by volume, or density is mass by volume to the power minus 1. Right. So this can be written as, if we are going to differentiate that, d rho by rho is equal to m minus m dV by V. Okay, it will be minus m dV by V. How to do it? How to get this relation? Okay, same thing as we did in errors case, if you remember. Delta rho by rho equal to, this is minus dV by V. Same way. So here dV by V's place, I can write d rho by rho also. B d rho by rho equal to pressure. Yes, we can do that. Remember this relation also along with this, because sometimes they ask you question on this also. Okay, this is bulk modulus. Let's see a few questions on that one. External pressure is this, beta is this. What is percentage increase in volume of body? That means he is asking delta V by V from us. Okay, so what is the relation? Beta equal to P external, and here comes delta V by V. So delta V by V actually is P external by beta. Okay, P external is 10 to the power minus 2 Pascal by 1. That's it. Okay, this is delta V by V, but he is asking percentage change. Percentage change means I have to multiply with 100. So if you multiply with 100, it will come 1%. So change in volume in percentage is 1%. Okay. Second one, what is the percentage change in density of the body? So here delta V's place, we can write density also. So d rho by rho is equal to P naught by beta. He is asking change, percentage change. See? No change in that one. Whatever is the value here, same is the value for density also. Correct? Okay. Then density of water is 1000 kg per meter cube at the surface of water. Bulk modulus given 10 to the power 5. What is density of water at 100 meter depth? What is density of water? What relation we have? Relation we have is d rho by rho equal to P by beta. Okay, so d rho by 1000 equal to P. Now P where? At 100 meter depth. 100 meter depth means what pressure? Rho GH. Because change delta P, always remember this is what actually delta P. So on the surface of water is P naught. At 100 meter depth it will be P naught plus rho GH. What is delta P? Rho GH, because that is only going to increase the density. Okay, so rho GH by beta. Okay, so d rho is 1000 into again 1000 to 10 into 100 by beta, 10 to the power 5. Okay, so 3 zeros and 2 zeros, and this is cancelled. So 10 to the power 4. So d rho is 10 to the power 4. But is he asking d rho or is he asking density? Density. So let's write here. Rho final minus rho initial equal to 10 to the power 4. What is rho initial? At the top. So rho final is, this is 1000, okay? 1000 plus 10 to the power kg per meter cube. So that will be the density at 100 meter depth according to the given data. Okay. Modulus of rigidity that we have discussed already. Eta equal to F by A theta. Okay. We are moving ahead. Energy stored. Now, whenever you are going to stretch any wire or you are trying to produce the deformation in any object, you have to work, right? So, when you work, energy is stored. Just like spring is there, when we try to stretch the spring, spring energy is there, stored inside it, half kx square. Same here. Okay, so first thing what I am going to do is I am going to compare spring and this elastic wire. Okay, so in spring, restoration force is what? K into change in length of the spring. Restoration force is this. In wire, what is restoration force? What is restoration force? What we can say? So what we know is delta L by L equal to F by AY. So see now, what is restoration force value? Restoration force value is AY by L into delta L. So if I am going to compare these two, I can say spring constant is actually YA by L. YA by L. And since we know spring energy is half K delta L square, same way in wire's case, I can write half YA by L into change in length whole square. Correct? Clear? This is energy stored in wire. Few more forms are there in which we write this energy stored. What is that? We write this energy as half stress into strain into volume. This all I am telling you about wire only. Okay. So here Young's modulus only will be applied. This is Young's modulus. I am not talking about anything else. Only for wire. Okay. So half stress into strain into volume, or energy stored per unit volume is half stress into strain. So these are the formulas. But main is this. All these are coming from here only. Half kx square, and k is YA by L. Okay. This is energy. Let's see what questions are there. What is the energy stored by wire due to its own weight? Okay. So we know that energy is stored in this case. I'm not going to do it with half k delta x square because it will be slightly longer. Two steps will be more. So it's better that we'll do with half stress into strain into volume. Stress into strain into volume. What is stress? Mg by A. Weight of the wire by area. Strain is what? Delta L by L is what? How much? We have already done, right? Delta L we have found mgl by 2ay due to the wire. Here only. Okay, I'll show you where it is, where we have done. Oh, here. See? Because of own weight. What is the change in length? mgl by 2ay. Same thing we'll keep here. Okay. Here. So strain is mg L by 2ay. Now strain means delta L by L. So I am writing mg by 2ay. And here is volume. Volume is what? Area into length. So area you can cancel. That's all. M square G square L by 4ay. That's the energy. Simple. Okay. Then twisting of wire. Twisting a wire means if this is cylindrical wire and you are going to twist it like this, you hold it and twist. So what will happen when you apply the force on this one? How you are applying the force? Tangential force only, no? On the surface. On the surface you are applying the force. So tangential force. The tangential force means you are actually trying to produce the shear stress, shear strain. Okay. So what happens is when this you applied the torque you applied in this one because you are twisting. So when you applied the torque, this point, let's say A, move to A dash. Okay, you applied like this. So what is the angle created here? Yes. Maybe this angle is theta. We are calling it as angle of shear. But how much is the twist you have given? This is angle of twist? No. Angle of twist is always measured from the center. So for that we have taken this angle. Can you see that? From the center you join this one, from the center you join this one. So this angle is angle of twist. So if this is theta and here let's say I am saying is alpha. Okay, so what is theta actually? Theta is A dash by length. This is length. Okay, A dash by L. And what is this alpha? Alpha is A dash by R. So angle of twist depends on radius and angle of shear depends on length. Okay, remember that. On this itself, question will be asked. Sometimes theta by alpha, alpha by theta, something. Okay, and then final thing. Which one is easy to twist? Hollow one, hollow pipe or solid pipe? Answer is hollow pipe is difficult to twist. Solid one is easier to twist. Okay, hollow one is difficult to twist. Solid one is easier to twist. Remember that. Okay, clear? How it is? Because twist means is the torque that you are applying, right? So in this one, torque is directly proportional to theta actually. And torque is equal to c theta. And this is torsion constant. This is torsion constant. Okay, and torsion constant for hollow pipe or a hollow cylinder is more as compared to solid one. So because of this, more torque is required to twist hollow one as compared to solid. Right. So this is it. That's it for this chapter. Okay. So day 8, properties of solids is over. Thank you, students.